Hello everyone. Today we're going to talk about the energy and power of signals. So we define energy and power for arbitrary signals. I am Touri, and I am with the electrical and computer engineering at UCSD. So you've seen in your circuits classes that we define the power, instantaneous power, going through a resistor to be the product of the voltage and the current that is going through this resistor. And it would be V square if the voltage across the ports is V, then the instantaneous power would be V square over R for a linear resistor R. Or alternatively, you can actually write this as R times I square as V equals Ri. So if I have a time varying voltage across the port, again the instantaneous power is going to be V square over R, and or R times I square T. And the power consumption over time is defined to be the energy. Motivated by this, and many examples in engineering domains, including mechanical engineering, where we have the power, again, the instantaneous power, for example, proportional in some settings, proportional to velocity square. Motivation by these examples, we define, and this is very important that we're defining here, the energy of a continuous signal to be over a given interval t1 to t2 to be the integral of absolute value of xt square over this interval. Okay, so we're given an interval, the power, the energy over this interval would be the integral of the absolute value of the signal square. And this is very important that we're dealing with absolute value, because in general we're dealing with complex valued signals. So the square, the absolute value of xt is meaningful in that setting. Similarly, we define the energy of a discrete time signal xn over a discrete time interval n1 to n2, which is the set of all the integer values that are less than or equal to n2 and greater than or equal to n1. We define it to be the summation of xn absolute value square, where n ranges from n1 to n2. And we can define the average power of a signal to be the energy over a given interval divided by the length of the interval. And in the discrete time, the same way, the energy over the given interval divided by number of points in that interval. One thing to note that is that the number of points in the n1, n2 interval is n2 minus n1 plus 1, because we are also including the beginning point of this interval. So if n1 is negative 1, n2 is 1, we have 3 points, negative 1, 0, and 1 in these intervals. And we define the instantaneous power to be basically the absolute value of the signal square. So if we let the length of the interval, or actually that interval, go to infinity, the resulting quantity is called the total energy of the signal. And the same thing in the discrete time setting. So if you let n to go to infinity, the summation from negative n to n of absolute value of xn squared is called the total energy. So this total energy is always defined, right? Because we are integrating a positive signal. It might be infinity, but it is always well defined. So it is either finite or infinite. And we say that a signal is a finite energy signal if this energy value, the total energy value, is less than infinity. So let's look at one example So where xt equals e to the negative 1 plus jt, and we are interested in computing the total energy of this signal. To begin with, we look at the absolute value of xt for all t's. So absolute value of xt equals e to the negative 1 plus jt, and I can distribute again 1 plus jt, which is equal to t plus jt, and we use the product rule for exponentials, so it's equal to the absolute value of e to the negative t times the absolute value of e to the negative jt, which here we use the identity that absolute value of z1, z2 equals absolute value of z1 times absolute value of z2, which is quite a useful identity. So here what we get is that this is equals to absolute value of e to the negative t plus absolute value of e to the negative jt. So absolute value of e to the negative jt, again, it's useful to think about e to the jt as a vector on the complex plane that is on the unit circle with the angle t. So e to the negative jt would be the vector on the complex plane with the angle negative t. So quite naturally, the angle, so the vector is on the unit circle, so its absolute value is 1. And the absolute value of e to the negative t, e to the negative t is always a positive signal, positive value, so the absolute value is going to be e to the negative t. So therefore, the integral would be e to the negative t, the total energy is going to be e to the negative t square, which is e to the negative 2t dt. You may be tempted to say that e to the negative 2t, the integral, is going to be finite, but always have this in mind that exponentials, the pure exponentials always extend to minus infinity and positive infinity. In this case, e to the negative 2t, the value is actually, as t goes to negative infinity, e to the negative 2t goes to infinity. So the value of this integral is going to be infinity, and hence this signal, the total energy is infinity, and this signal is not a finite energy signal. Okay, so this is it for the definition of energy and power of a signal. Thank you for watching this video.